There are two types of energy involved in an orbit, potential energy and kinetic energy. And from physics class, you probably already know what those things are. But the equations for those are slightly different with respect to orbits. So write those two words down, and we will use these energy relationships to determine how to transfer a satellite into a new orbit. Woo! So potential energy is energy that is stored within a system due to the position of the system. And it has potential to convert into other energy forms. Kinetic energy is energy of motion. So again, potential energy is stored energy. Kinetic energy is energy in motion. Those are two key ideas to write down. Both are important to satellite orbits. The gravitational pull of the Earth, as something is orbiting around it, we have this orbiting around. The gravitational pull is the potential energy, and the satellite movement has kinetic energy. Here's your equation for gravitational potential energy. It is U equals negative GMM over R. So I'd like you to pause this now. Go ahead and write down that equation and then all of these values here. So let's take a look at a problem for gravitational potential energy. A shuttle with a mass of 103,000 kilograms is flying 370 kilometers above Earth's surface. And roughly 100 kilometers is kind of the barrier for what we would call space, although it's very fluid. How much potential energy does it have? We're also given the mass of the Earth. We need to know that. And the radius of the Earth is 6.378 times 10 to the third. Or you could also identify this as 6,378 kilometers. Now, one really important thing to note on this, when we go back to this equation, we need to know the radius, how far away we are from it. You have to include the radius of the Earth in that, and the units for that are meters. So our next problem was given in kilometers. We have to convert that to meters. And gravitational constant is a given, and the mass of the central body, that's the Earth. Then we have the mass of the orbiting body is m. So we have everything. We have the mass of the orbiting body. We have how far away it is in kilometers. The radius of the Earth in kilometers. We add these together, and then we have to convert to meters, and then we just plug them into the equation. So here's our equation, and plugged all in. Here's the g value, and here's the mass of the Earth. Here's the mass of the satellite, and then we're adding up the the distances of the Earth, because the radius of the Earth, that's how far we are from the center of it. The center of the Earth to the edge of the Earth is this value, and then the surface of the Earth, or the edge of the Earth to the satellite, is an additional this value here. So we convert all these into meters, and they're showing it in scientific notation. A lot of times I'll just write it out as 6,378,000 meters plus, in this case, it would be 370,000 meters, and add those together. So the hardest part about these problems is most people just try to type them all in at once and then push enter and then just hope. That's not going to work. You're better off finding the numerator, writing down the answer to that, finding the denominator, writing down the answer to that, dividing them, and then don't forget the sign. The sign is important. So what you should end up with is a negative 6.1 times 10 to the 12 joules. That's how much potential energy this thing has. If it were to just come crashing down into the Earth, that would be a lot of energy. We have an asteroid approaching. Kinetic energy is energy of motion, 1/2 mv squared, and that is very similar to the equation that you've seen in physics class, where m is mass, v is velocity. So if you have a satellite traveling 6 kilometers per second and has a mass of 5,000 kilograms, what amount of kinetic energy does it have? Remember, units matter. So mass has to be in kilograms. Velocity has to be in meters per second. So we have to convert that. So when you write down this equation and you write this down, what you should add after each of these, kinetic energy, mass, and velocity, is a unit. So kinetic energy is joules, it's energy, mass is kilograms, and velocity is meters per second. So make sure that you put those units down for this. So we have to convert kilometers per second into meters per second. So it's times 1,000. That's why it's 6 times 10 to the third, or 6,000 is 6 kilometers per second and 6,000 meters per second. So we plug all those in, and you end up with 9 times 10 to the 10th joules. So now we can look at the total energy of an orbit if we just combine the potential and kinetic energies. So remember, if a satellite is orbiting around the Earth, then, or any body for that matter, then it has potential energy because it's away from the Earth. It has a distance away from the Earth. If it's moving, it also has kinetic energy. So if we combine those, that's the total energy. So E is what we call total energy. It is U plus K. Remember, this is the equation for potential, this is the equation for kinetic, and if we add these two together, we get this. What? Where'd that come from? How do you get this from this? Well, I'm going to show you. So get ready. In circular orbits, the force of gravity between a planet and the sun is gmm over r squared. That is just an equation that you probably have seen in physics class. You might not have seen it yet, but if you have, yay. So that's one thing that we know. The force of gravity between the planet is this. Gravitational force also equals centripetal force. The force that's attracting something has to be equal to the centripetal force, which is the force that is kind of pushing it away at all times. That centripetal force is the force that's pushing out against the gravitational force. If they're equal, it stays in perfect orbit. If gravitational force wins, it slowly gets closer. If centripetal force is bigger, it slowly gets further and further and further away. If they're equal, it's a steady orbit. So we're going to say that we have things in a constant steady orbit. So we're going to say that these have to be equal. And since we're saying they have to be equal, gravitational force, which is the equation I just said here, is this. This equation for centripetal force from your physics class and experimentation is mv squared over r. And so if gmm over r squared equals mv squared over r, if we multiply both sides by r, what happens to them? You get rid of one on each side. So now instead of mv squared over r, we just have mv squared. And instead of over r squared here, we just have r. So we're saying that these are really the same as this. Good so far? If not, raise your hand and call me over and I'll help you out with this. So we know that mv squared equals gmm over r. Well, guess what? Look at this mv squared. I can take this mv squared and I can replace it with what it's equal to, which is this, gmm over r. So I'm going to take the gmm over r and put it right here. You ready for it? All right, I pushed that in. So now you have E equals minus gmm over r plus 1/2 mv squared. Just look at this one piece here. That's this equation we started with. We're going to substitute in for that mv squared, this gmm over r, that piece. So now we have a minus gmm over r plus 1/2 gmm over r. Or minus 1 gmm over r plus 1/2 gmm over r. If we have a minus 1 and a half, we end up with a minus 1/2. If we take a minus 1 and we add a half to it. So that minus 1/2 then becomes a minus gmm over 2r. That 1/2 just means a 2 in the denominator. So that's where we end up with, when we add these together, we end up with a minus gmm over 2r, which is that equation. Nailed it! So if we want to calculate the changing orbit altitude, how much energy is needed to travel from one orbit to another, you have to figure out the orbit energy at one spot and then the orbit energy in another spot, and then subtract them. That'll figure out how much energy is needed. We have a news station that wants to move a 12,000 kilogram weather satellite from 650 kilometers. Remember, you have to convert that to meters. Really note that in your notebook, because that's something that most people will miss on the test or on their assignments here. You got to convert these to meters. And you want to move it to 800 kilometers above the Earth's surface. So how much energy will this procedure require? How much energy do we have to put into this? Because if we're going away from Earth's gravity, we have to add energy to get this to happen. So if we're going to figure this out, we have to figure out the total energy of it to begin with. So to figure out that total energy, that's minus gmm over 2r. So we don't even have to worry about the velocity anymore, because we solved total energy is now this equation. So velocity is embedded into this, along with potential energy, kinetic energy, it's everything, it's total. So this one is our constant. We have our mass of the Earth, we have mass of the satellite, and then we have the r, which is the radius of the Earth plus the height, which is 650 kilometers, or 6.5 times 10 to the 5th meters if you go back. That's this value right here. Then we are finding our second energy, where we're trying to end up, is the same thing, same numerator. That's why I suggest doing the numerator separately, over 2 times the radius, but this time the satellite altitude is at 800 kilometers, or 8 times 10 to the 5th meters. So that's the only difference between these. To change the orbit, we take 2 minus 1. So right now, I want you to pause this. I want you to type this out on your calculator, write down the answers in your engineering notebook, and see if you get what you get for E2 minus 1. So please pause that now and check for value for E1, E2, and then your total. It's really important that you actually do this work and not just move on, because you're not going to know if you're doing it right. You can say, oh, I know how to use a calculator, but you have to try it on your own. Now you can see I wrote down every single thing here. You don't want to round this until you're done. You want to round your final answer, not individual answers. So that's my value for E1. E2 is this. If we subtract them, we end up with 7.1 times 10 to the 9th after we use significant figures here. So don't apply significant figures until the end. The positive sign signifies that energy must be added. If you are increasing in altitude, you have to add energy into that system. So I'm hoping that you did this in your calculator and you actually try this out. If you didn't get this answer and you're not sure why, call me over and I'll help you out with that. Now, for review, you've learned some of the basic physical properties involving in transferring orbits. Potential and kinetic energy are two main orbital energies. You combine both to find the total energy of an orbit, and with both orbit energies, you subtract them to determine the energy to transfer between orbits. So your only other scenario, so here's a little picture. If we start here and we want to end up at this orbit, then we would find the energy required at the larger green orbit, subtract it from the yellow orbit, and that's the energy needed in this red transition. If we go the other direction, from green to yellow, then we are subtracting energy. We're releasing energy. So it's going to be a negative value. So those are a couple key points to remember. Now it's your turn to try to practice this.